Hi, this is Dr. John Bergdorf. This video is entitled A Library of Functions. So we're in a section of the course where we have been and we're going to continue to be talking a great deal about the graphs of functions. It turns out that there is a relatively small collection of well-known functions upon whose graphs many other functions in their graphs can be built. If you know the members of what I'm going to call this library of functions, you can often graph many other functions by using some transformational techniques, or even when you can't use that, there's still a good deal of inspiration in these graphs that give you an idea of how to graph functions that are similar in one way or another. So I want to introduce you to my library of functions, many of which have names. And the first one we're going to start off with is very simply called the identity function. And it is defined by the equation f of x is equal to x. Now, for this and all of the other functions we're going to look at, we are simply going to start graphing them by just building a plain old table of values where we select some values of x, and we plug them into the equation, and we find the corresponding values of y. And the numbers I'm choosing here, you're going to get tired of because I'm going to suggest them all the time. They're basically smallish numbers in absolute values, some positive, some negative, to get a good sense of the shape. Now, the equation is f of x equal x. F of x means the same thing as y, so what we're saying is that y equal x. This is called the identity function because it leaves all the values unchanged. The y matches the x. If we plot those points over on my Cartesian plane over here, they would look like this. Negative 2, 2, negative 1, 1, 0, 0, 1, 1, 2, 2. And it's pretty obvious what this is beginning to look like. It is a straight line. It passes through the origin. Well, not supposed to have that little wiggle like it has at the end. It's supposed to be a straight line. And we're going to see this line on a number of occasions. A way to describe it is that it passes through the origin at a 45-degree angle from the x-axis. Very important graph. And actually, even if you had not plotted points, you might have recognized that this graph falls into the general form for a line. If you think about slope-intercept form, this is slope-intercept form where the m happens to be 1 and the b is 0. So that would be a line with a y-intercept of 0, and that definitely is the case, and a slope of 1. Write that as 1 over 1, and that tells you that the line goes up 1 over 1, up 1 over 1, up 1 over 1, and that's really, really clear. Now, as simple as that is, if you can just know and just have it deep in your soul that f of x equal x, that the graph of that function is this straight line at a 45-degree angle, you've got it made. You don't even have to think about it anymore. I have a more professionally drawn graph over here. This was created by the program Desmos, which does a wonderful job of graphing functions and other relations for that matter. And it's pretty easy to use. It's also free. I'm suggesting that when you see f of x equal x, you just remember that it is this line at a 45-degree angle through the origin. And if you want to plot some points, now that we know what's going on, just these very few points would be enough to get you the shape. We know that 2 points define a line. There's 3, an extra one. Again, that's called the identity function. Let's look at another one. This one's called the squaring function. We're going to spend a lot of time on functions that are built on this function. Called the squaring function very simply because the equation is defined by f of x equal x squared. I'm going to graph this by the very old-fashioned method of picking some values for x, plugging them into the equation, and getting the value of y. So the equation is given by in this case, for example, f of 2 would be negative 2 squared, the entire quantity, negative 2 times negative 2. That would give me a 4. If x is negative 1, y would be negative 1 squared. That's 1. If x is 0, y would be 0. If x is 1, 1 squared is 1. 2 squared is 4. Let's see what that graph looks like. So negative 2, 4 would be right there. Negative 1, 1 is here. 0, 0, 1, 1, 2, 4. And you can kind of see that this would be something like a U shape. Like that. Kind of missed that point a little bit. We'll just kind of broaden it a little. That shape is called a parabola. We're going to spend tons of time talking about parabolas, as it turns out. And again, if you just sort of keep in mind a couple things, you can get the graph of f of x equal x squared very quickly. Once you believe that the equation will be a parabola, really all you need to do is just plot a few points. I'm going to suggest only 3, and just remember that the graph will pass through these points. So here's just 3 simple points from the table on the other page. And you can see in this graph right here that they all work. Negative 1, 1 would be right there. 0, 0 is here. 1, 1 is there. If you know the basic shape, you're going to have, this will be plenty. Just get those 3 points and know that you're creating a parabola shape through them, and you're good. So know the identity function, the line at a 45-degree angle. Know the squaring function of parabola. What about f of x equal x cubed? That sort of makes sense. We've looked at x, x squared, x cubed. Well, again, let's just plot points. Pick the same values for x. These are just great values for x. Small, easy. Negative 2 cubed would be negative 2 times negative 2 times negative 2. A negative times a negative times a negative is a negative, and 2 times 2 times 2 is 8. So negative 2, negative 8. Negative 1 to the third. Negative 1 times negative 1 times negative 1, that gives you negative 1. 0, 0 times 0 times 0, that's 0. 1 cubed is 1, positive 1 though, and 2 cubed would be positive 8. Let's plot those points. Negative 2, negative 8 goes slightly off the bottom of my graph. This only reaches down to 6. I'm going to estimate that negative 2, negative 8 would be about there. Negative 1 is here. 0, 0 is here. 1, 1 is there. And 2, 8 would be, again, we'll sort of estimate it right about up there. And once you've plotted a few points, you connect those up with a reasonable curve. This looks like it sort of comes up in a interesting flowing pattern, levels off, makes this funny little wiggle here near the origin, and takes off again. It's unfortunate that no one has ever really determined a specific name for this shape. We're going to see it's the common shape for the graph of f of x equal x cubed. Some people call this simply a wiggle. I've heard it called a snake, but if you don't like snakes, that's not a good choice. See, that's not very elegant. I once suggested to a class that wiggle would sound a whole lot better if it were translated into Latin, say. And I had a student who checked that out, and the Latin term for wiggle is crispico. So I had a class full of students who referred to these as crispicos. But that's not agreed on by anyone. There's no agreed upon shape. You can get this general shape, again, if you focus on 3 points. You'll see this when we talk about transformations later. I'm going to suggest that for all of these basic functions in the library, if you can identify 3 points and then know basically what the shape is, that will be more than enough to get a decent sketch. And you can graph many more complicated things. So notice for my key points from the other examples too, what I'm always doing is I'm just thinking about what do I get when I plug in negative 1, 0, and 1? Just what does that give me? And that gives me these points right here. And then I remember to create this wiggle, this snake, this crispico that goes through those shapes. Now here's an interesting thing. If you look at this table and compare it with this table for the identity function, notice the ordered pairs are the same. So just having the ordered pairs is not enough. You have to know the ordered pairs and what shape you're going to end up with depending on the graph. So this gives a more of a wiggle shape. Okay, let's look at some more. Square root of negative x. So I'm going to start with my usual numbers, negative 2, negative 1, 0, 1, 2, and look at those. So f of negative 2 would be the principal square root of negative 2, which is not a real number. We know we can express that in terms of I, but where would that go on the graph? Well, the sort of implied thing behind the Cartesian plane is that you're looking at real numbers only. So if you plug in a value for x and you get an imaginary number, it's really not a point that you can graph. So there's actually not going to be a point that you can plot with negative 2. That will be relevant when we plot some points. Negative 1, same problem. Square root of negative 1 is I. Can't plot that point. 0 is okay. The principal square root of 0 is 0. And the principal square root of 1 is 1. Principal square root of 2 is something. I'd have to use a calculator. You might just bear in mind that there's nothing terribly magical about these numbers that I've chosen for my table. If I get a number, if I choose a value for x that's just not all that convenient, you can always change it. I'm going to suggest maybe we look at a 4 instead, because the principal square root of 4 would be 2. So here's the points that I end up with. 0, 0, 1, 1, 4, 2. And you can kind of see a shape developing there. It probably goes off like that. And you might be tempted to say, okay, now what happens? Does it go this way? But it doesn't, because what we discovered is when we tried to substitute in negative values for x, we got values that were not real numbers that cannot be graphed. So there can't be any part of this graph over here where the x values are negative. Let's erase that. That can't happen. And so you might ask, well, does it turn around and go like this maybe? But two problems with that. First of all, it would no longer be a function. And second of all, we should have gotten those y values when we plugged in these x values, and we didn't. So it doesn't do that either. It just is that much. It sort of begins at the origin and goes from there. I'm going to call it a swoosh. Again, not an agreed upon mathematical term. This is the first one of the graphs we've looked at that's had a limited domain and range, by the way. If you think about this, the domain of this graph is simply 0 to infinity, and so is the range. So there's a restriction on the domain and range. That's the square root function. Now if I change the square root to a... Oh, I forgot. I was going to show you again. So how do you create this when you want to do this fast? Well, again, just a few points. If you use the key values of negative 1, 0, and 1 that we've been talking about, the negative 1, as you can see, is going to give you something that cannot be graphed. I'm going to claim it's good enough just to know those 2 points. As long as you know that the graph goes through 0, 0 and 1, 1 and has this swoosh shape to it that you're seeing, that is really quite enough to get the sense of what that graph looks like. 2 points and the knowledge that it's going to be a swoosh. What if we had a cube root? Wonder if it does the same thing. So before we get too involved in this, and thinking maybe it does, let's pick some values of x. I'm going to start with the usual values of x. But right away I realize I have something that just doesn't look like it's going to be a lot of fun. The cube root of negative 2, don't know what that is. I'm totally free to change these x values to something else. And if I were to change that x value to negative 8, The cube root of negative 8, that's what number do you raise to the third power to give you negative 8? That would equal negative 2, and that would be a point on the graph. So that is, first of all, a real number. So this function is defined for negative values of x. It gives me an actual point. That point would be roughly right about there. If I plug in a negative 1, the cube root of negative 1 is negative 1. The cube root of 0 is 0. The cube root of 1 is 1. And then I might as well change this 2 to an 8. And the cube root of 8 is 2. Plotting some of those points. Here's the negative 8, negative 2. There's negative 1, 0, 0, 1, 1. And 8, 2 will kind of be right about there. Now, if you look at that, erasing some of the stray marks that I made, that looks a whole lot like the wiggle shape that we saw for f of x equal x cubed, except instead of opening upward, it opens sideways, a sideways wiggle. Or a sideways crispico, if you prefer. If I want to, once I know what that looks like, again, just a few key points are enough. And notice that these are the same, some of the same ordered pairs we've seen before, but as long as we know that the graph goes through those points, negative 1, 0, 0, 1, 1, and has this sideways wiggle shape, or sideways snake, or sideways crispico. So it's important to check a few points, but it's important to have a good sense of what the graph of each function looks like. Absolute value. Okay, this graph is very, very interesting. Let's plug in some values for x again, and we're going to go back to the usuals. When you look at the absolute value of a number, remember that's the distance between that number and 0 on the x-axis, on a number line. And so the absolute value of negative 2 is 2. The absolute value of negative 1 is 1. The absolute value of 0 is 0. Absolute value of 1 is 1. Absolute value of 2 is 2. Let's plot those points. Negative 2, negative 2. Negative 1, negative 1. 0, 0. 1, 1. 2, 2. And you know what? If we wanted to go a little bit farther on, this graph would have negative 3, 3. Positive 3, 3. Negative 4, 4. Positive 4, 4. And I wanted to do that to show that whereas at first glance you might think, oh, it's another parabola, notice that we don't have those gently swooping branches that we have in a parabola. Instead, the two branches, let's say, of this absolute value function are very sharp straight lines. So they are going to end up meeting at what we might call the vertex in a sharp angle. And this is very simply called a V shape. Again, knowing just a few key points and the fact that the graph has a certain shape, you believe and you know that that graph will be a V shape. Just a few values of x and y to get your bearings, and then the knowledge that you want to connect them up with a V-shaped graph. That is plenty to get the shape of that graph. Now, what we've looked at so far, the graphs we've looked at so far, are the main members of my library of functions that I want to talk about. There is one more that's rather peculiar, and I want to look at this one. It's called the greatest integer function, and I'm handling this one a little bit differently. I'm going to talk about what it means, and then we're just going to look at the graph more quickly. We're not going to spend a lot of time on this one. That odd-looking symbol like that means the greatest integer less than or equal to x. How does that work? Well, let's suppose you're making a table. And I'm going to be much more picky about this one. So I'm going to pick 0, and the y value here would be the greatest integer that's less than or equal to x. Well, 0 is less than or equal to itself, and that's an integer. So that would give me an x. Give me a 0. Now, look at what happens if I pick something like 0.5 or 0.9 or 0.99. The greatest integer that is less than or equal to 0.5 is 0. Greatest integer less than 0.9 is 0. Greatest integer less than or equal to 0.99 is still 0. Now, as soon as x gets to 1, the greatest integer less than 1 is 1. And then 1.1 would give you still 1, and 1.7 would give you 1, greatest integer less than or equal to. That creates a very surprising graph. And I want to focus just for a minute on that little piece right there. What that's saying is that for every value of x between 0 and 1, the y values all turn out to be 0. But when you get to 1, the graph like hops up and hits a y value of 1. You might remember from a previous picture that this open circle here means that the point is not included. A solid point means that the point is included. And so the bottom line for a greatest integer function is you get basically what looks like a staircase. Little steps 1 unit wide, and then you go up and up and up and up like that. Very curious graph. Now, perhaps with the least attention being paid to greatest integer functions, if you look at this, you will have a sense of a number of graphs that you hopefully will just know. You'll look at the equation and immediately recognize, oh, that's a parabola. Oh, that's a V-shape. Oh, that's a wiggle. And by just plotting at most 3 points, you'll have enough to get a sketch of that graph. And upon those graphs, we will build many, many transformations over the next few days. So, I hope that sounds like fun.